All right, so welcome to my series of videos on statistics. And in this video, I'm going to teach hypothesis testing for true population variance. But before then, in the former video, I should have added this particular slide, but let's add it to this particular video. It doesn't fit. Now, we have done hypothesis testing for a single population variance. That's what we just did in the former video, okay? Now, it means you can also find a confidence interval. You can find the confidence interval for a single population variance. So this is the formula, n minus 1 times the sample variance all over the chi-square of the upper bound. So this here, so like the example we did, the chi-square of the upper bound was 16.978 or 16.98. All right. No, it was 16.68, sorry. So the example we just did, the upper bound was 19.68, sorry, all right? So let's try and construct a confidence interval for the example we just did. Let's try and construct a confidence interval, okay? Let's try and construct a confidence interval. Now here, the formula for confidence interval for a single population variance is n minus 1 sample variance all over the chi-square of the upper bound less than or equal to population standard deviation less than or equal to n minus 1 sample standard deviation over chi-square of the lower bound. So we are using this same example to do it, right? Remember the population variance was 36. Okay, so we bring it to so less than or equal to the sample size was 12. So here we have 12 minus 1. Okay. Then the sample variance was 26.6. All over the upper bound of the chi-square. The upper bound of the chi-square, remember, was 19.68. Okay. So less than or equal to here, n minus 1, 12 minus 1, 26.6. Then the lower bound of the chi-square was 4.58. Okay, so let's do our computations. So if you punch the left-hand side, 12 minus 1 is 11. So 11 times 26.6, everything divided by 19.66, you get 14.87, right? Where is less than or equal to 36? And it's less than or equal to here. If you multiply the 11, 12 minus 1 is 11. You multiply by 26.6 divided by 4.58, you get 63.89, all right? So here, because the question was 90% confidence, you can say that the 90% confidence interval is between 14.87 and 63.89. So it's between these bounds, okay? The 36 there is just to confirm the answer. The reason why we put the population standard deviation in the middle is just to confirm the answer, all right? So that's the 90% confidence interval. Now, the next thing we are going to discuss is confidence interval and hypothesis testing for true population variance. Confidence interval and hypothesis testing for true population variance. Now, when it happens like this, okay, confidence interval for true population variance as well as the hypothesis testing, here we are not going to use the chi-square table. We are going to rather use the F table. So here we are going to use the F table instead of the chi-square table, all right? We are going to use the F table instead of the chi-square table. We are going to use the F table instead of the chi-square table, okay? Now, this is the formula for finding your own computed F. Your own computed F is the sample variance of group 1 divided by the sample variance of group 2. All right. And then, of course, for you to get your critical F, we will read from a table. So we need degree of freedom. So degree of freedom for group 1 will be n minus 1. Degree of freedom for group 2 will be n minus 2. All right. So let's get into the interesting stuff now. Now, F distribution is formed by the ratio of two independent chi-square variables. F distribution is determined by its degree of freedom. The assumption is that populations are normally distributed and the samples are randomly and independently selected. Now, here we are going to learn how to formulate or read the F ratio. So here, to use the F distribution table for a two-tailed test, listen carefully. Always place the larger sample variance in the numerator. All right. So because the formula is variance of the first group divided by the variance of the second group, always you determine what the first group is and you determine what the second group is. So always make sure the one that has a bigger variance is the first group. So that will be the numerator. Then the sample variance that is smaller will be the denominator. This will make the calculated F value greater than 1.0 and push the F value toward the upper tail of the F distribution. All right, we are going to do an example so you get it clearer. For the one-tailed test, examine the alternative hypothesis for the population that is predicted based on alternative hypothesis to have a larger variance. Place the sample variance, place that sample variance in the numerator. So let's listen carefully. It says, for the one-tailed test, examine the alternative hypothesis. So when it is one-tailed, what it means is that we rather test the alternative hypothesis, not the null. And it says, for the population that is predicted based on the alternative hypothesis to have the larger variance, place the sample variance in the numerator. Place that sample variance in the numerator. So here also, we're going to place the larger one in the numerator, all right? But we are going to test it. When we are testing this, we test it on the alternative, not the null. All this while we have been testing the hypothesis on the null. But for a one-tailed F distribution test, we test it on the alternative. Okay. So that is what it's saying. All right. So when it is a two-tailed test, okay, when it's a two-tailed test, this is how it will be. We have to divide the alpha by 2 as always. When it's a one-tailed test, this is how it is. All right. So let's look at this. Now the steps are that. So let's look at an example. Transportation agency is concerned about the waiting time for passengers, who use the downstairs transit center. Of particular interest is whether there is a difference in the standard deviations in the waiting time that occurs A and B. All right. So remember, for any test of difference, the default null hypothesis is that there is no difference between the two groups, the default. Then the alternative is that there is what? A difference. There is a difference, all right? Now, so our F table is what we are going to read now. Now, let me take time to explain how to read the F table. It is quite interesting. So if you don't pay attention, you mix it up, all right? Now, to read your F table, you always need degree of freedom in the numerator, and you need the degree of freedom in the denominator. Okay. If you are lucky, usually in exams, the critical F will be given so that you just compare. all right? Mostly to be given and you just compare. But then if you want to read the critical F value, you need to know the number of degrees of freedom in the numerator and the number of degrees of freedom in the denominator, all right? So the figures here, 1, 2, 3, 4, 5, 6, 7, 8, 9, they are the number of degrees of freedom in the numerator. Then the figures here, 1, 2, 3, 4, 5, 6, 7, they are the number of degrees of freedom in the denominator, okay? They are the number of degrees of freedom in the denominator. Now, we also have the p-values here. This signifies the alpha level of just one of the tails, okay? This signifies the alpha level of just one of the tails. So 0.100 here means that just one of the tails is 0.1. That means the two tails is 0.2. All right, that means the alpha is 0.2 and then the significance is 0.8. All right. 0.05 here simply means that one of the tails is 5% or 0.05. It means the two tails combined will be 0.1. But here, listen carefully. The values here is just for just one tail. All right. So don't confuse yourself. And when you are given a question, if it is one tail, you can read directly. If it is a two-tail question and they gave you alpha in the question, divide by 2 before you come and read it from here. All right. Because these figures here are just the critical values of just one tail. So if one of your tails is 0.1, this is it. If it is 0.05, this is it. If it is 0.25, this is it. If it's 0.010, this is it. And if it's 0.0010, that's that. Let me go over again. What I said was that if one of your tails is 0.1, you read it from the first line. If one of your tails is 0.05, you read it from the second line. If one of your tails is 0.025, you read it from the third line. If one of your tails is 0.10, you read it from the fourth line. And if one of your tails is 0.001, you read it from the fifth line. Now, this particular question we are solving, it is a two-tailed test. And we are testing it at alpha is equal to 0.02. So we want to know what one of the tails is. So one of the tails will be 0.01, all right? One of the tails will be 0.01. So keep in mind that we are reading an alpha of 0.01 because the F table there, it just gives the values for one of the tails. It doesn't give value for two of the tails, right? Okay. Now, remember that the degree of freedom of the numerator, because the numerator is group 1. So group 1, the sample size is 31, and its degree of freedom is 30, because the degree of freedom is sample size minus 1. So that is it. So group 1, or the numerator, its degree of freedom is 30. Then for the denominator, its degree of freedom is 24, all right? Its degree of freedom is 24. Its degree of freedom is 24, okay? Now, how do we come about this? In the question, the sample standard deviation for group B is 4.79. That means that the sample variance for group B is 4.79 squared, okay? And then the sample standard deviation for group A is 3.77. That means that the sample variance for group A will be 3.77 squared, all right? So we have 4.79 squared. That is 22.944. Then 3.77 squared, that is 14.2129. All right. Now here we don't respect whether it's A or B. if you remember, the slides or the notes said that always the bigger one should be the numerator, all right? So we are going to compute the F, the bigger one will be the numerator. So it means group B will be the numerator, all right? Then group A will be the denominator because the bigger one will be the numerator, all right? So you have 22.9441 all over 14.2129. Okay, so 22.9441 all over this. We're going to get 1.16. Sorry, 1.6. We're going to get 1.614. Okay, so this is the computed F. This is the computed F. Now we are going to read the critical F from the table. But before that, we need the degree of freedom of the numerator. So degree of freedom of the numerator is sample size of group B minus 1, because group B is the numerator. And the sample size of group B was 31. So minus 1 is 30. And then group A is the denominator. So the degree of freedom of group A is the sample size, which is 25 minus 1. So it is 24. Okay, so the degree of freedom of the numerator is 30. Degree of freedom of the denominator is 24. And remember, we are testing that alpha is equal to 0.02. It means that one of the tails is 0.01. All right, let's keep this in mind. One of the tails is 0.01. And remember, the chi-square table, we always read one of the tails. Okay, so let's go to, sorry, the F table, not chi-square, the F table, we normally read one of the tails. So let's go to the F table. So here, one of our tails is 0.01. So you'll be concerned with this one. So everything here is repeated. The reason why these values are repeated is that it gives us all possible levels of alpha, as well as all possible degrees of freedom. Okay, so if the degree of freedom of the numerator is 1 and the degree of freedom of the denominator is 1, and the alpha of one tail is 0.1, then this will be the figure. So if the alpha of one tail is 0.1 and the degree of freedom of the numerator is 1 and the degree of freedom of the denominator is 1, then it means that this will be the critical F. Okay, but in our instance, the degree of freedom of the numerator is 30. So you're going to look for it. You scroll down. So you get to the point where we have degree of freedom in the numerator, you find 30, okay? So degree of freedom of the numerator is 30. So here, degree of freedom in the numerator is 30. So we have it here, all right? Then the degree of freedom of the denominator is 24, all right? Is 24. Now, here, this table here, or this page is repeated in the next page. So this table, we have degree of freedom in the numerator from 1 to 9. And then degree of freedom in the denominator from 8 to 16, right? So in the next page, it didn't write degree of freedom in the denominator because it's assumed that it will be repeated. So in the next page, the first set of figures here is for degree of freedom of the denominator of 8, because 8 is here. All right, 8 is here. So when the degree of freedom of the denominator is 8, it is the first one here. The second set here is for degree of freedom of 9. The third set here is for degree of freedom of 10. The next one is a degree of freedom of 11, all for the denominator. So the table doesn't want to repeat itself, like repeating the 8, 9, 10, blah, blah, blah. So everything here is 8, 9, 10, and on and on. But then The change between this page and the next page is that the degree of freedom of the numerator has changed. So the former one we had 1 to 9. The next one we have 10 to 1,000. Okay, so here, although the degree of freedom in our numerator is 30, we will not have degree of freedom in our denominator 24 to be here because we only have 8 to 17 repeated. So here is 8, 9, 10 up to 17 repeated. So now let's go on still. So as we move along, we now have degree of freedom of the denominator. We now find the 24, all right? We now find the 24. So 24, we now find the 24. And let's count it. 24 is 1, 2, 3, 4, 5, 6, 7. The seventh set of figures, all right? When we go to the next page, it will not repeat the 24. So we have to know that it is the seventh set of figures. So let's go again. So now we now have the degree of freedom in the numerator to be 30. And the 24 will be found here. So the 24 was the seventh set of figures. So we have first set of figures, second set of figures, third set of figures, fourth set of figures, fifth set of figures, and now we have the sixth set of figures. Then, so let's go again. This is the first set of figures. Okay. The first set of figures is number 18. The second set of figures is number 19 for the denominator. The third set of figures is number 20. The fourth set of figures is number 21. The fifth set of figures is number 22. The sixth set of figures is number 23. The seventh set of figures is number 24. Okay. So we now have 30 here as against 24. So it should be found here. Now, even with that, it can be 1.67, 1.94, 2.2, and 2.58, and 3.59. But remember, this set of figures, the fourth one from the beginning, I told you that the fourth one is the one that has one tail to be 0.01. Okay, so the fourth one. So here, eventually, the figure we will pick is 2.58. All right, so the F value is 2.58. So when you draw, because it's two-tailed, you will have negative 2.58 here, 2.58 here, all right? And here is the acceptance region, and then here is the rejection region. Here is the rejection region, okay? Here is the rejection region. Now, our computed F was 1.614, okay? So if you bring it on the graph, it will fall within, 1.614 will be within. So our computed F is 1.614, which is within the bounds, all right? So here you just conclude by saying that we fail to reject the null hypothesis because the computed F, which was 1.614, is less than the critical F, which is 2.58, okay? Therefore, so when we fail to reject the null, remember when you fail to reject the null, this was the null hypothesis. When you fail to reject the null, it means your conclusion will be in the null, all right? So here, we just say that we conclude that therefore, there is no difference in the variances, all right? So I know reading of the F statistics table is pretty confusing, but please go over the video so many times. I believe you can get it, all right? So in my next video, I'm going to teach on analysis of variance, all right? So kindly like, share, comment, and most importantly, subscribe to my channel for more content. I'm going to provide a link in the videos where you can download all the files I have been using to teach in the video, all right? All right, thank you very much for appreciating my page. Thank you.